Today we shall discuss motion in one dimension. Let us look through some basic terminology in this chapter. First, what is rest? Rest and motion, these are terms which are well associated with any object moving with respect to its surroundings or is at rest with respect to its surroundings. So specifically, rest means if a body is not changing its position, with respect to its immediate surroundings, then the object is at rest. And if an object changes its position with respect to its immediate surroundings, then the object is in motion. An object at rest, an object in motion, these are terms which are purely relative, which means that these terms are truly dependent on the observer who is observing the given situation. Say for example, if someone is standing in a railway platform, with respect to him or her, a nearby tree is at rest. But when a train leaves the platform, definitely the train is in motion with respect to that observer. However, with respect to the passengers in a moving train, if someone within the train tries to look out of the window, they will see the trees are moving in the opposite direction. So with respect to the passengers in the train, the trees are in motion, but with respect to a passenger who is on the railway station, with respect to him, the tree is at rest. So there are several examples where we can relate rest and motion, but they are purely relative or dependent on the observer. So if an observer does not observe any change in position, then he or she will say that the object is in rest. And if an observer measures some change in position, then he or she will say that the object is in motion. The planets are in motion with respect to any observer on the earth. But with respect to observers on the earth seems to be at rest, whereas we know that the earth is spinning with respect to its own axis, but we cannot realize it because we are observers on the earth itself. So there are several situations where we can relate rest and motion, but they are not absolute rest or absolute motion. They are purely relative and dependent on the observer who is analyzing the situation. Now, motion is of three types. It is either one-dimensional motion, or two-dimensional motion, or three-dimensional motion. If an object is restricted to move along a straight line path, then its motion is one-dimensional motion. Motion along a straight line path is also called as a rectilinear motion. There are several examples related to one-dimensional motion. For example, if a vehicle is moving along a straight path, a stone is falling vertically down. These are examples which we can say is motion along a straight line path. Whereas motion along a curved path is called two-dimensional motion or curvilinear motion. The motion of any object which is along a curved path is two-dimensional motion. For example, the motion of a crawling insect on a wall is two-dimensional motion because the insect need not always follow a straight line path when it crawls on the wall. Whereas if the motion is in space, then it is called as three-dimensional motion. For example, if an insect is flying within a room, then its motion is three-dimensional motion because the insect need not move in a straight line path or a curved path, but it is covering the entire space that it gets in order to fly. In this chapter, we will restrict our discussion to one-dimensional motion only. So, with respect to one-dimensional motion, some important terms we have to realize. The first one is the distance. What is the distance? Distance refers to the actual length of the path traversed by a body. So actual length of the path means the nature of the path that the object will follow when it moves from one position to another position. When it moves from one position to another position, it might follow a straight line path, it might follow a curved path, but the nature of the path should be realized whenever we are trying to measure the distance. So we say that the actual length of the path will be called as the distance traveled or distance traversed. It is a scalar quantity, which means that distance has only a specific value or magnitude, it has no specific direction. Next, we have to realize what is displacement. Displacement is totally path independent. It does not depend on the path followed by the object when it moves from one position to another position. And so, displacement is nothing but the shortest distance from the initial to the final position. And it's a vector quantity. Vector quantity means those quantities which have both magnitude and direction. So, whenever we try to represent displacement, along with its value, we have to indicate the proper direction, which is from the initial to the final position. Now, if you compare distance versus displacement, we can realize that the magnitude of the displacement, which is the shortest distance, is either equal to the distance or less than the distance itself. Because magnitude of displacement may be equal to the distance provided the body is moving along a straight line path. And if a body changes its position along a straight line path between the initial and the final position, the shortest distance is equal to the distance itself. However, if the body is moving along a curved path, then the distance traveled is actual length of the curved path, whereas the displacement is the straight line distance that connects the initial position to the final position. And so, in this case, if a body moves along a curved path, the magnitude of the displacement is always less than the distance followed by the body. Now, if an object starts from a given position and returns back to the same position, traveling any path, then its displacement is zero. Because we realize that the object has not changed its position. It has started from the same position and ended at the same position. But it might have followed a definite path, so distance is not zero, definitely. Distance is in that respect always positive because it has a specific value. However, displacement can be negative, positive or zero. Depends upon the direction associated with displacement. Whenever we are saying that displacement is negative, we mean it's the direction that is negative. It is not the value that is negative. The value is always positive, but the direction might be in the opposite sense, and that's why it is taken to be negative. We will take some examples later. So finally, we can realize that distance depends on the path followed, which I have already told, but the displacement is path independent, and so it is measured by the shortest distance. We will take some examples in a short time. Let us take some examples of distance and displacement. First, basic example. Suppose a body is moving along a straight line path. Say for example, the body is moving along the x-axis. The body is moving along the x-axis. Suppose the body was initially at the point O, and after some time it has reached the point P. And in this process, the straight line distance from O to P is say 5 cm. In this case, the distance travelled is obviously the length of the path OP, the length of the straight line OP, or the length of the line segment OP. We can write it as OP line segment, which is obviously 5 cm. Because the object is moving on a straight line path. And the displacement is also the shortest distance from the initial to the final position. So along a straight line path, the shortest distance is the straight line distance itself. So displacement has its magnitude 5 cm. The magnitude or the value of the displacement is 5 cm, but its direction is, say we have to write in this form, along positive x-axis. Because we have taken this example as the body moving from O to P along the positive x-axis. So we say the direction is along the positive x-axis. In order to represent the displacement direction, the direction of any physical quantity which is a vector, we can also consider the geographic directions. Let us take another example. Suppose a body has started its journey from the point O. It has moved along east 4 cm and reached the point B. Then along north it has moved a distance 3 cm and then finally stopped. So O to B is 4 cm, it is due east, and then 3 cm due north. So the initial position is O and the final position is say P. So what is the distance traveled? In this case, the distance is actual length of the path, which is obviously OB plus BP, which is 4 cm plus 3 cm, that is equal to 7 cm. But the displacement is the shortest distance between the initial and the final position, which will obviously be the straight line distance OP. So displacement has its value or magnitude equal to the shortest distance. Now we see that this is a right angle triangle, and so 3 square plus 4 square, square root of that will give you 5 cm. So displacement has its magnitude 5 cm, and in order to represent the direction, we can say it is moving along OP. And in terms of the geographic direction, we can say it is moving along northeast, because if this is 3 cm, this is 4 cm, this is probably some angle which is greater than 0 but less than 90 degrees. So you can say that it is more or less around the northeast direction. So for the time being, I am writing it as direction OP, along OP. We can take further examples also. You can note it down. Suppose a body is moving on a circular path. It has started its journey from the point A, moved in a clockwise manner, and finally reached the point A. It started its journey from point A, moved along a circular path in clockwise direction, and again finally stopped at the point A. So because its initial and final position remains the same, we can say that the displacement is 0. Displacement is 0. But the distance is actual length of the path traveled. So the distance will be equal to the circumference of the circle. Distance is equal to, suppose the radius of this circle is say r, then the distance traveled is equal to 2 pi r. So in this case, you see that the displacement is less than the distance traveled. In the previous case also, the displacement was less than the distance traveled, and in the first example that I took, the distance was equal to the displacement. So however, displacement is always less than or equal to the distance traveled. Let us take another example. Suppose a body moves along a semicircular path. It starts its journey from the point O and reaches the point P. And this arc OP is say a semicircle. It has moved in this specific direction from O to P along a semicircular arc. Say the radius of this arc is 2 cm. So the displacement is obviously the shortest distance between the initial and the final position, and the shortest distance will be equal to this line segment OP, and that will be equal to twice the radius. That is 2 into 2, that is 4 cm. That means the diameter of this semicircular path. and it is the shortest distance. The straight line distance is always shortest distance, and the distance is equal to the actual length of the path. We know that the circumference of a circle is 2 pi r, so the circumference of a semicircle will be pi into r. So this will be pi into 2. You can take pi as 3.14. So that is approximately 6.28 centimeter. Now we discuss speed and velocity. Speed and velocity of a body. Speed of any object or any body will demonstrate its motion, and while demonstrating its motion, speed will refer to the distance travelled in a given interval of time. So speed can be defined as rate of change of distance covered by the body in a given time interval. Actually, whenever we say it is the rate of change of distance, it automatically means that the distance is being divided by the time interval during which the body remains in motion. So simply we can say that speed is equal to the distance travelled in a given time interval. Speed is obviously a scalar quantity. While measuring speed, we are not concerned about the direction of motion, and so speed remains to be a scalar quantity. Mathematically, you can say that the speed is the distance travelled in 1 second. If time is 1 second, then the corresponding distance travelled and the value of speed will remain same, because if time is 1, speed is equal to distance. So speed can be referred to as distance travelled in a given unit time interval. Obviously, the SI unit and CGS unit, the SI unit of speed is meter per second and the CGS unit is centimeter per second. However, the speed can be either uniform or non-uniform. So when we say that the speed is uniform, it means that the body is travelling equal distances in equal time intervals. If a body travels in such a manner that it covers equal distances, if equal distances are covered in equal time intervals, then the speed of the body is uniform, or you can say it is constant speed. The speed might be non-uniform or variable. Then the body will travel unequal distances in equal time intervals. If unequal distances are covered in equal time intervals, then the speed of the body is non-uniform or variable. You can say it is variable also, because it is varying with time. As the distances are unequal, but the corresponding time intervals should be equal. Remember that equal distances in equal time intervals is uniform speed. Unequal distances in equal time intervals is non-uniform speed. For example, of uniform speed, you can say that the motion of any object which is rolling on a floor, which is frictionless, then the speed is more or less uniform. But if a body is moving along a straight line on a rough floor, then its speed is non-uniform. We can take an example here. For uniform speed, an object moving in a straight line on a frictionless floor. Frictionless floor. In reality, it is very difficult to realize a surface which is frictionless, but for the sake of an example, we are considering that the object is moving on a straight line and if you take the example of non-uniform speed, we can say that the object is moving, an object moving on a straight line on a rough floor. That means some amount of friction is present on the floor. Then you can say that its speed is non-uniform. There are varieties of examples in reality where we come across non-uniform speed. For example, the motion of a car in a crowded street, the motion of a train which is leaving or approaching the platform. There are various such examples of non-uniform speed. Now, whenever a body is moving with a non-uniform speed, we have to define what is called as instantaneous speed and average speed, because we cannot calculate the exact amount of change in speed or change in distance that has occurred in the given time interval, because by how much distance the body travels in the given equal time intervals, it might be difficult to analyze. So we have to define what is called as instantaneous speed. Until the speed is uniform, until the speed is non-uniform, if the speed remains uniform, then you can easily say that uniform speed is equal to distance by time. So whenever the speed is uniform, then we can say that distance traveled is equal to speed into time. This formula is applicable. If we denote distance by s, speed by v, and time by t, then distance equal to speed into time is valid, provided the speed is uniform. However, if the speed is non-uniform, then this cannot be precisely said. So in that case, we have to define what is called as instantaneous speed. So what is instantaneous speed? If you go by the literal meaning, it refers to the speed at a given instant of time. But because the speed is continuously changing with time, speed at any instant or a particular moment of time will be called as instantaneous speed. Whenever we try to measure instantaneous speed, we have to divide the entire distance traveled by the body into a large number of small distances. The entire distance traveled by a body has to be divided into a large number of small distances, and then if we divide those small distances by the corresponding time interval, then what we get is called as the instantaneous speed. So instantaneous speed can be defined as ratio of distance traveled in a very small time interval. Ratio of distance traveled in a very small time interval to that corresponding small time interval. Corresponding small time interval. This small time interval should be as small as possible. So, instantaneous speed and uniform speed have no relation. Instantaneous speed is defined whenever the speed is non-uniform or variable. In that situation, we can also define what is called as average speed. Now, while measuring average speed, we do not divide the entire distance into a large number of small distances. However, what we do is we divide the entire distance traveled by the body divided by the time interval that has elapsed when the body has covered that given distance. So, average speed is simply total distance traveled by the body by the total time interval, the total time taken by the body to cover that distance. So, on an average, you can say that the value remains the same throughout, but actually the speed is changing, and so average speed will not give you the correct picture of the motion. It does not convey the actual message regarding the motion of the body, because the speed is changing in different time intervals, and so you can say that more or less the body has maintained its average speed throughout the journey, but the actual speed can be sometimes lesser than the average speed, sometimes it can be greater than the average speed. So, average speed is only an approximate value for the speed of the body which is moving with a non-uniform speed. Now, the instantaneous speed and the average speed might be same. So, if a body is moving with uniform speed, if a body is moving with uniform speed, then we can say that its instantaneous speed and the average speed produce the same result. If a body is moving with uniform speed, then instantaneous speed so if the body is moving with uniform speed, then instantaneous speed is equal to the average speed. Remember that this is a truth whenever the body is moving with uniform speed only. Otherwise, the average speed and the instantaneous speed are never same. If the body is moving with non-uniform speed or variable speed, then obviously instantaneous speed and average speed will produce different results. But only if the body is moving with uniform speed, then only this is applicable. Now, the speedometer of a vehicle measures the instantaneous speed. The speedometer of a vehicle measures instantaneous speed, because whenever a vehicle is moving, definitely its speed is continuously changing with time. So at every instant, the speedometer will record a different value of the speed, and that's why we say that the speedometer of a vehicle measures instantaneous speed, never the average speed. Obviously, speed is a scalar quantity, and so average speed, instantaneous speed, non-uniform speed, uniform speed are definitely scalar quantities. Now we should discuss velocity. The velocity of a body can be defined as the rate of change of displacement. rate of change of displacement in a given time interval. So you can just say that the velocity is displacement divided by the corresponding time interval in which the displacement has occurred. Again, like speed, this result produces an average value. Now, we can also say that velocity is the distance traveled by a body in a given time interval in a specific direction, because displacement is nothing but distance traveled in a specific direction. So, you can say that the velocity is the distance traveled by a body in a given time interval in some specific direction. However, because the direction is involved here, velocity is a vector quantity, and velocity and speed all have the same units. Because the unit of displacement remains meter, the unit of time remains second, so its unit is either meter per second in SI units or centimeter per second in CGS unit. So in a similar manner, we can also define what is called as uniform velocity. Uniform velocity is when the body undergoes equal displacements in equal time intervals. If a body is in motion in such a manner that it covers equal displacements in equal time intervals, then we can say that its velocity is uniform. We can also say that equal distances covered in equal time intervals in some specific direction will produce uniform velocity. In a similar manner, we can also define what is called as non-uniform or variable velocity. Non-uniform velocity or variable velocity. And then, just as we defined in the case of non-uniform speed, we can say that unequal displacements covered by the body in equal time intervals. Equal time intervals. Now, while measuring non-uniform velocity, it is not only unequal displacements. This is just for the sake of a definition that we say that it is unequal displacements in equal time intervals, or you can say that the body is moving in such a manner that it has travelled unequal distances in equal time intervals in a specific direction, that is non-uniform velocity. But because velocity is a vector quantity and displacement is also a vector quantity, it might happen that the direction of motion of the body is continuously changing. Then also, it is quite possible that the velocity becomes non-uniform. For example, of motion, where a body is moving with uniform velocity, you can say that a raindrop which is reaching the earth's surface is more or less uniform velocity. This is not absolutely true, but on an approximate basis we can say that when a raindrop is released from a cloud, it reaches the earth's surface with a uniform velocity. Actually, what happens is that for a certain time interval, when the raindrop is just released from the cloud, it accelerates, its velocity changes with time, but after some time, the forces acting on the raindrop counterbalance each other in such a manner that the raindrop achieves a constant or a uniform velocity, and that uniform velocity is also called as terminal velocity of the falling raindrop. So, for an example, on an approximate basis, you can say that for example of uniform velocity, a raindrop reaching the earth's surface. Reaching the earth's surface. But mind it, it is not purely uniform. We just on an approximate basis discuss the following raindrop as a motion of uniform velocity. And non-uniform velocity, there are several situations where a body is moving with non-uniform velocity. A body moving on a circular path has its velocity as non-uniform, because in that case the body might possess the magnitude of the speed or the magnitude of the velocity as same, but because its direction is continuously changing, the velocity is non-uniform. Non-uniform velocity is also an example where in different situations where a body is freely flowing under gravity, its velocity is non-uniform. For non-uniform, you can say that a freely falling body is acted upon by the Earth's gravitational pull. Because it is acted upon by the Earth's gravitational pull, its velocity increases at a constant rate, and so the velocity is non-uniform in that situation. In case of circular motion, body moving on a circular path, the velocity is variable. Suppose the body is moving on a circular path in such a manner that at every instant of its journey, the velocity has the same value. Suppose the velocity is v at the point A on the circular path. Let me assume that the body is moving in anti-clockwise manner. At some other point B, the velocity is having the same magnitude v, but its direction is continuously changing, and so this is an example where the speed is uniform but the velocity is variable. Here it is not the displacement that is taken into account. The direction of motion is changing at every instant of time, and that's why we say that the velocity is variable due to the change in direction of the motion only. Its magnitude, that is the speed, that remains constant, that is same everywhere. The velocity at any instant of time or any point of the circular path, the velocity is along the tangent. And if you draw a tangent at any point on circular path, obviously the direction of the tangent will continuously change. So because velocity is always tangential, the velocity is variable due to change in direction. So if we are talking about non-uniform velocity, we should again take into account what is instantaneous velocity and what is average velocity. Instantaneous velocity. Just as we have defined in the case of instantaneous speed, instantaneous velocity is the velocity at a given instant of time. Given instant of time. So while we are trying to measure the velocity at a given instant of time, we have to divide the distance travelled by the body in a given direction into a large number of small distances of displacements, and we have to divide those displacements with respect to the very short time intervals concerned in the journey of the body. So you can say that instantaneous velocity is ratio of very small displacement or very small distance covered in a specific direction to the very small time interval that we have taken, time interval. The time interval is so small that the direction of motion has not changed in that time interval, and on that basis we define what is called as instantaneous velocity. Just remember that the time interval is so small that during that time interval the direction of motion has not changed at all, and so you can say that instantaneous velocity is the ratio of the very small displacement that might occur in the given very small time interval. And then its average velocity, where we just consider the entire displacement of the body throughout the journey and the corresponding time interval. So you can say that it is the net displacement or the total displacement and the total time of the journey. The body has started its motion. We have assumed that the body is moving along a straight line. So from the starting point to the finishing point, we just measure the displacement and we divide it by the total time taken, and then what we will get is called as the average velocity. The average velocity of a body can be 0, but its average speed may not be 0. This is a point to be noted, that average velocity can be 0, but average speed may not be 0. For example, if a body starts from a point and it comes back to that same point, suppose the body starts its journey from point A, it follows some specific path in a given direction and it returns back to the same point A after some time interval. In this situation, the displacement is 0 because the starting and the finishing point remains the same, and as displacement is 0, displacement divided by the time interval, that is the average velocity, is 0. However, the distance traveled is not 0 because this entire path length has to be considered when measuring the distance, and obviously the body has taken some time to come back to its initial position. So because distance is not 0, distance divided by time is not 0, and so average speed is not 0, but the average velocity is definitely 0. This is also possible in the case of circular motion. If a body is moving with circular path and it is covering equal distances in equal time intervals, the speed is uniform. That we have already discussed. Suppose a body is moving on a circular path and it is covering equal distances in equal time intervals such that its speed is uniform. The speed is having the same value at every instant of time at every point of the journey. The value is v at every point of the entire circular path. So the speed is uniform, and if we measure the average speed, then it is the speed divided by the time interval. But the average velocity may not be 0. Now it is a matter of concern from where the body starts its journey. Suppose the body starts its journey from the point A, it follows the circular path in a anti-clockwise manner, it again comes back to the point A. Then obviously the displacement is 0. In that situation you can say that the average velocity is 0. But in this situation, if the body starts from this point and comes back to this point again, then it has covered a distance that is equal to the circumference of the circular path. And so average speed is distance by time, and so average speed is not 0, but the average velocity is 0. The instantaneous speed in this situation is not 0. The instantaneous velocity is also not 0, because the instantaneous speed and the instantaneous velocity, they depend on a very small time interval in the entire journey. So suppose the body is moving on a circular path, it starts from this point, it is moving and then it comes back. In between the starting and the finishing position, at any point, if you consider, suppose at the point B, if you try to calculate what is the instantaneous velocity or the instantaneous speed, it is never 0. But the average speed is non-zero and the average velocity is 0, provided the body has started from the same point and covered the circular path and reached back to the starting point again. The average displacement is 0. In that case, you can say the average velocity is obviously 0 because displacement is 0. But the average speed is equal to the circumference of the circle. Say this is the center of the circle and its radius is r. Then the average speed is the total distance traveled by the total time taken. The time taken for the entire journey is equal to the time period of the revolution. Suppose, let me consider this is t, which is obviously not 0. So when the speed of when the velocity of a body is non-uniform, it means that the velocity is changing with respect to time. Now, change with respect to time is either the change in its magnitude or the change in its direction. So, because velocity is a vector quantity, change in velocity might refer to change in direction, change in magnitude, or both. So whenever the velocity is changing with respect to time, what we get is called as acceleration. If the velocity of a body changes either in magnitude, velocity changes. The change is either in magnitude, that means the value of the velocity is changing, or the velocity is changing in direction. Velocity changes means its magnitude changes, or its direction changes, or both is changing simultaneously, or both are changing simultaneously. So when the velocity changes, it might increase with respect to time or it might decrease with respect to time. If the velocity is increasing with respect to time, we say that the body is accelerating. So acceleration is obviously a vector quantity and it is equal to the increase in velocity in a given time interval. And similarly, if the velocity is decreasing with respect to time, then we say that the body is retarding. So retardation is the decrease in velocity in a given time interval. We know the SI units of velocity and time, so we can say that this acceleration has SI unit, which is obviously the SI unit of velocity by time, that is meter per second divided by second, that is meter per second square, and the CGS unit is centimeter per second square. Acceleration is obviously a vector quantity because it is defined as change in velocity. Velocity is a vector quantity, so acceleration is also a vector quantity. There are a variety of examples where the motion of a body is an accelerated motion. A body falling from some specific height and reaching the earth's surface is obviously accelerating. Whenever we try to project a body with some velocity above the earth's surface and it reaches a specific height, its velocity is decreasing with respect to time. That example is an example of retarded motion. The velocity of a vehicle in a busy or crowded road, where its velocity is continuously either increasing or decreasing at different time intervals, that is a partially accelerated or partially retarded motion. So there are a variety of examples. Now, with respect to the acceleration and retardation, we can actually have a mathematical statement of this form. Suppose the initial velocity of a body is u. Suppose initial means at t equal to 0. At t equal to 0, initial velocity, which is the velocity at t equal to 0, let me denote that velocity as u. After time t has elapsed, after time t, the velocity changes, and suppose the velocity has increased to v. Then the acceleration, let me denote it by a. This acceleration is equal to increase in velocity by time. So if you cross multiply it, then write at equal to v minus u, which means u is taken to the right hand side. So v equal to u plus at will be the equation that establishes the relationship between initial velocity, final velocity, acceleration and time taken. So this is an equation which is valid for a body moving with variable velocity and constant acceleration along a straight line. So whenever a body is moving with some acceleration, obviously this a is positive. But if the body is retarding, that means its velocity is decreasing with respect to time. In case of numericals, we have to replace a by minus of a. So for uniformly accelerated motion, v equal to u plus at. For uniformly retarded motion, the value of a will be negative because the velocity is decreasing with respect to time. Suppose a body is falling freely. Whenever it is falling freely, it is under the effect of the Earth's gravitational pull, and when it is under the effect of the Earth's gravitational pull, it is accelerating, and that acceleration is said to be g, or the acceleration due to gravity. The body is falling from some height. Say the body is falling from some height h above the Earth's surface. Object is dropped with certain velocity. It might have the initial velocity, it may not have some initial velocity. But if a body is falling under gravity from some height, then this equation will take this form, v equal to u plus gt, because the acceleration is the acceleration due to gravity. However, if the object is thrown upwards from the ground surface, it is thrown upwards with some velocity from the ground surface, because the Earth's gravitational pull is in the vertical downward direction, the value of g has to be taken as negative for vertically upwards direction motion. Vertically upward. If the body is moving vertically upward, then in place of g we will write minus g. So the equation will become v equal to u minus gt, because its velocity is continuously decrease with time as the earth is pulling the body. Its motion is a uniformly retarded motion. Actually, the value of g is taken to be constant at a value that is 9.8 meter per second square. But the value of g is not practically constant. On an average basis, we say that the value is 9.8 meter per second square. Sometimes approximately we take it as 10 meter per second square. But the value of g depends on altitude and depth. So g decreases with altitude or height above the Earth's surface and depth below the Earth's surface. decreases with height above the earth's surface and it also decreases with depth below the earth's surface. The value of G on the earth's surface is also not uniform throughout. It is maximum at the poles, and it is minimum at the equator. G is minimum at the equator. But for numericals or mathematical calculations, we take the average value of G as 9.8 meter per second square. Now, we can relate the different parameters of motion that we have already discussed. Like we have related velocity with acceleration and time, we can also relate displacement with these corresponding quantities. So, remembering this equation V equal to U plus AT, if a body is moving with constant acceleration, then you can say its displacement equal to average velocity into the time taken. If the displacement is denoted as S and the average velocity is equal to U plus V by 2. Remember that U is the initial velocity and V is the final velocity. So average value we are taking as U plus V by 2. So now this formula, displacement equal to average velocity into time, this is only applicable provided the body is moving with a constant acceleration. Our equations of motion for one-dimensional motion will be always with respect to motion with constant acceleration. If the acceleration becomes variable, then you cannot use this elementary form of mathematics to represent the motion. So S equal to U plus V by 2, S is the displacement, average velocity is U plus V by 2, U is the initial velocity, V is the final velocity and T is the corresponding time interval. Now we have already deduced V equal to U plus AT. So since V is U plus AT, we will substitute this value of V here. So what we get is S equal to U plus, instead of V, U plus AT by 2 into T. So cross multiplying, this is 2S, this is U plus U, 2U plus AT into T, which gives 2S equal to 2UT plus AT square. 2S equal to 2UT plus AT square. So now we divide this equation by 2. So we divide this equation by 2. One can write this S equal to this one by 2, that is 2UT plus AT square by 2, which means S equal to 2UT by 2 plus AT square by 2 . This gives S equal to 2 and 2 cancels out, UT, and instead of writing AT square by 2, we will write it as half AT square. So this is the second equation that we have to remember for numericals. The first was V equal to U plus AT and the second is UT plus half AT square. Again, if the motion is a motion with uniform retardation, then A will be simply replaced by minus A. So for motion under gravity, if an object is being dropped from some specific height, if an object is dropped from a height, then G is positive. Object dropped from height with velocity U. after some time t it gathers velocity v. So in that case your g is positive. So this equation will become, instead of height h, we will write this as h equal to ut plus half gt square. So displacement will be replaced by the height and acceleration will be replaced by g, that is the acceleration due to gravity. And if the object is thrown upwards, object thrown vertically upwards, with initial velocity u, then g will be taken as negative, and so if the object reaches some height h in time t, then you will write h equal to ut minus half gt square. So remember, for acceleration a and g are both positive, for retardation a and g are both negative. So the same equation, just displacement is replaced by height, acceleration is replaced by g. Now we have to derive an equation where we will try to eliminate time. We will relate the initial velocity, the final velocity and the displacement only. So we will start with this equation and we will try to relate u, v and s by eliminating time. So we start from this equation, s equal to ut plus half at square, and we know v equal to u plus at. So we can write v minus u is at, or t equal to v minus u by a. So this we will substitute here. So what we get is u into, instead of t we will write v minus u by a plus half a, v minus u by a whole square, s equal to, here in the denominator you have a square and a in the numerator, one a will cancel out and in the denominator you will have a. So taking LCM you will get 2a. So 2 will be multiplied here, 2u into v minus u plus, there is no a because a square versus a has cancelled out. So this is just v minus u square. So s equal to, we just expand these terms, 2uv minus 2u square plus v minus u square is v square plus u square minus 2uv by 2a. So from here you see 2uv and minus 2uv cancels out, and plus u square minus 2u square, you will get just a single minus u square, and this 2a will cross multiplied, so we get 2as on the left hand side. 2a into s is 2as. So if we rearrange this, we can write v square minus u square is 2as. You can remember this in this form, or you can say by taking u square to the right hand side, v square equal to u square plus 2as. Again, for motion under gravity, if an object is falling from some specific height h with initial velocity u, a will be replaced by g and s will be replaced by h. And if an object is thrown with some velocity u and it reaches some height h, then the equation will be v square equal to u square minus 2gh. So for motion under gravity, it's quite simple. We have to replace with g and take positive or negative sign for accelerated or retarded motion. All these equations that we have derived can be approached in a graphical manner, but for that we have to understand graphical motion, which I will discuss later. So for motion under gravity, if the body is falling down from some height h, with initial velocity u. The equation will be v square equal to u square plus 2gh, because h is positive, g is positive. And if the body is moving upward, it reaches height h, its starting velocity is u, or initial velocity is u. Here g is negative, so we get v square equal to u square minus 2gh. Vertically upward motion is retarded motion, vertically downward motion is accelerated motion. Let us solve two numericals. The first numerical is a car travels fast 30 km with uniform speed of 60 km per hour and the next 30 km with uniform speed of 40 km per hour. It has been asked to calculate the total time and the average speed of the car. So the first time instant, let me call it as t1, 30 km traveled with uniform speed 60 km per hour. Time is distance by speed, so this is 30 km divided by 60 km per hour, which will become half of an hour, that is 0.5 hour. The next time interval is with respect to uniform speed of 40 km per hour and the same 30 km has been travelled. So the next time is t2 is 30 km per hour divided by the speed, that is 30 km divided by 40 km per hour, which is 3 upon 4, 3/4 of an hour, which is 0.75 hour. So therefore, the first part of the question, that is total time, say t, must be equal to t1 plus t2, that is 0.5 plus 0.75, which is 1.25 hour. Now 1.25 hour, you can convert it to minutes. Now 1 hour is 60 minutes and 0.25 of an hour is 15 minutes, because we know that 1 hour is 60 minutes. So 1.25 hours you can convert and you will get 75 minutes. Now we have to calculate the average speed. So by the definition of average speed, we know that average speed is total distance by total time by total time. Total distance is obviously 30 plus 30 and total time is 1.25 hours. So that is 60 by 1.25 km per hour. Now this is equal to 60 into 100 by 125. If you cancel with 25, we get 60 into 25 into 4 is 100, 25 into 5. So this is 12 into 4, because 60 by 5 is 12. So this is 48 km per hour. The next problem is a car is moving in a straight line with speed 18 km per hour. It is stopped in 5 seconds by applying brakes. You have to calculate the speed of the car in meter per second, the retardation and the speed of the car after 2 seconds of applying the brakes. So first of all, we have to convert the speed into meter per second. So first part of the question, the speed is given as 18 km per hour. To directly convert into meter per second, you can just multiply by 5 by 18 and you will get your answer in meter per second. So this is 5 meter per second. Actually 5 by 18 is nothing but kilometer, 1 kilometer means 1000 meter and 1 hour means 3600 seconds. So if you divide 1000 by 3600, you will get 10 by 36, and 10 by 36 you cancel with 2, you get 5 by 18. So directly from kilometer per hour to meter per second you can multiply 5 by 18. Now the next is the retardation produced. Remember that in the question the car is moving with a straight line with speed 18 km per hour, which becomes 5 meter per second. This is the initial speed. So this can be written as 5 meter per second as the initial speed. It has been stopped in 5 seconds by applying brakes. Because it has been stopped, its final velocity v is obviously 0. And the time interval is 5 seconds. So from the relation v equal to u plus at, here we substitute v as 0, u as 5 and t as 5 seconds. So this means minus 5 equal to 5a, which means a equal to minus 1 meter per second. Whenever acceleration, the value we get in negative, it means there is a retardation. So we write retardation produced is 1 meter per second square. The acceleration is negative, it means that retardation is 1 meter per second square. Now the third part of the question, the speed of the car after 2 seconds of applying the brakes. Now when the brakes have been applied, it stops after 5 seconds. But after 2 seconds, its velocity is not 0. So in this case, u remains 5 meter per second. The velocity value is unknown. We have already calculated the retardation, that is the acceleration in negative form is retardation. So acceleration is minus 1 meter per second square. The time now is 2 seconds. The time given is 2 seconds. So again, if you use the same equation v equal to u plus at, instead of v equal to u plus at, v is unknown here. So v is u means 5 plus a means minus 1 and time is now 2 seconds. So this is minus 1 into 2. So 5 minus 2, this gives v equal to 3 meter per second. So it means that after 2 seconds the velocity is 3 meter per second. So this is the third part of the question. Now we will take a different problem and try to solve it. The question is, body moving with a constant acceleration travels distances 3 and 8 meter, 3 meter and 8 meter respectively in 1 second and 2 seconds. In 1 second and 2 seconds. It has been asked to find initial velocity and the acceleration of the body, and the acceleration, that is the uniform acceleration or the constant acceleration, which is unknown. You have to calculate that. So let us start with our basic equations. A body is moving with constant acceleration and its travelling distance is 3 meter and 8 meter in 1 second and 2 seconds respectively. So we have to choose an equation that relates distance travelled with time, initial velocity and acceleration. So our equation is S equal to ut plus half at square. Because S represents displacement or distance what we measure, U represents the initial velocity, A represents the acceleration and T as time. So from the first part of the question, that is, it is travelling with constant acceleration 3 meter in 1 second. So therefore instead of S we will write 3, instead of T we will write 1 and the other quantities are just variables. Sorry, 1 square. So this is 3 equal to U plus A by 2. If you take LCM, that is 2U plus A by 2, or you can say 2U plus A equal to 6. This is your first equation. Now the second part of the question, the same equation we have to apply. It is travelling 8 meter in 2 seconds. So instead of S we will write 8, instead of T we will write 2. So this we can simplify as 2U plus 2 square is 4, 4 by 2 is again 2A. If you take 2 common, so it cancels out and you get U plus A equal to 4. This is our second equation. Now from first and second, if you subtract equation 2 from 1, what you get is 2U minus U is U, A minus A is 0 and 6 minus 4 is 2. So you get U as 2 meter per second. So initial velocity is 2 meter per second. You can put the value of U in any of the equations. So let us put this value here. We will get 2 plus A equal to 4, which means your acceleration is again 4 minus 2, that is 2 meter per second square. So it's quite simple. So both the initial velocity and the acceleration have value 2, but units are different. It is 2 meter per second and the acceleration is 2 meter per second square. Let us take another example. This question is a bit lengthy. Question 4. We will try to solve it part by part. A spacecraft is flying along a straight course with a velocity of 75 kilometer per second. And it is firing its rocket motors for 6 seconds. After 6 seconds, at the end of this, its speed is 120 km per second in the same direction. The question has two parts. The first part is, it has been asked to calculate the average acceleration when the motors were being fired. find acceleration while the motors were firing. So spacecraft is flying along a straight course with a velocity of 75 km per second. It fires its rocket motors for 6 seconds, and at the end of this 6 seconds, its speed is 120 km per second in the same direction. You have to find the acceleration. So the simple equation that we can apply here is V equal to U plus AT. So the final velocity is 120 km per second, and the initial is obviously 75 km per second. Acceleration and the time is 6 seconds. So 120 minus 75 is 5, 45 equal to 6A, which means A equal to 45 by 6. 6 7 is 42, 30, 6 5 is 30, 7.5 km per second square will be the unit, because the velocity was given in kilometer per second, so the acceleration is 7.5 km per second. This is part 1 of the question. The second part is, it has been asked the distance traveled by the spacecraft. The second part of the question, you have to find distance traveled by the spacecraft in the first 10 seconds. 10 seconds after the rocket motors were started. And it has been said that the rocket motors were in action for only 6 seconds. Were in action for 6 seconds only. So to calculate acceleration, which we have already done, the second part is you have to calculate the distance traveled in the first 10 seconds after the rocket motors were started, but it is known that the rocket motors were in action for 6 seconds. That means for the first 6 seconds the body was accelerating, and when the rocket motors were shut down, the body started moving with a constant velocity, because if the rocket motors were shut, you have to remember that after 6 seconds the speed that the rocket has achieved will be the constant speed with which the rocket motors will move. There is no acceleration for the next part of the journey. For the first 6 seconds it is an uniformly accelerated motion. For the next 4 seconds it is a motion, it is a uniform motion. That means the velocity remains constant. So in the second situation, after 6 seconds had completed, the velocity we have to calculate. So after 6 seconds, we have already been informed that the velocity is 120 meter per second. So for the first 4 seconds, the distance has to be calculated. Sorry, for the first 6 seconds. 6 seconds. The distance can be calculated by using this formula. V square minus U square is 2s, or s equal to ut plus half at square. So let me use this s equal to ut plus half at square. So u is initial, that is 75. Time is now 6 seconds plus half into a, we have already calculated 7.5 into 6 square. Now 6 into 5 is 30, 3 is 45, 450 plus half into 6 square is 36, 36 by 2 is 18, so this is 7.5 by 18. For the next 4 seconds, it is a motion, it is a uniform motion. So for next 4 seconds, you can just apply the formula distance equal to speed into time, is equal to Vt. So here V is the final velocity that the body has achieved after 6 seconds, which is 120 meter per second, 120 kilometer per second, already provided. 120 into time 4. So this is 480 kilometer, and this is obviously in kilometer. So the total distance we have to calculate now. This value plus this value. So total distance sorry 7.5, 6 square is 36, 36 by 2 is 18, 18 will come in the numerator. So 7.5 into 18. So what we have is 450 plus 7.5 into 18. 18 into 5 is 90. So 7.5 into 18 is 135. 135 plus this is 480. So what we will get, 400 and 400 is 800, 800 plus 1 is 900, 900 plus 80, 980, 980 plus 50 is 1035, 30 plus 35, 1065 kilometer. So the total distance travelled is 1065 kilometer. So again, the problem was asked to calculate total distance travelled in 10 seconds, remembering that for the first 6 seconds it is a uniformly accelerated motion, for the next 4 seconds it is a motion with constant velocity. So there is no acceleration for the next 4 seconds. So distance equal to speed in time is applicable for the 4 second part of the journey.